Okay, we're going to talk about matrix matrix rank. And this gets a little bit theoretical. You need to understand the terms I defined and talked about in chapter 1 of where I talked about vectors and things like span, dimension, basis, space. What's the definition of the rank of a matrix? Any size matrix. We'll call it rank of A for the matrix A. It's the maximum number of linearly independent rows of A. Rows or row vectors in A. Each row of A can be considered as a vector. We talked about the span, right? The span of the row vectors, that's called the row space, kind of by definition. Thus, the rank, by this definition, means the dimension of the row space. It's the maximum number of linearly independent, or the minimum number of vectors it takes to span the space. So let's look at a couple of facts. First fact is that row operations, we talked about row operations, they maintain the row space and therefore the rank. Here's that basic linear combination of vectors. Now these R's are going to be the row vectors. Let's look at those row operations. If I just switch two rows, all I did was switch two things here. I mean, the space didn't change. It's still the same rows. If I multiply any row by a constant, it doesn't change. You know, we're going to test this and see if it equals 0 without all the C's being zeros. If I multiply any of these vectors by a constant, it really doesn't change things because I can make the C anything, right? So that doesn't change it either. And if we replace a given row, I'll say like replace row 2 by adding K times R1 to it. This is the arithmetic of this linear combination. It ends up being this. So it doesn't really matter because I can the C's or whatever I want to make them, and it's still the basic same linear combination when I consider all possible C's. So the row space does not change with row operations. So if the space doesn't change, neither does its dimension. Meaning the row operations don't change the rank of the matrix. And definition-wise, we say two matrices are row equivalent if one can be obtained by the same finite number of row operations. So row operations maintain rank. I can't say the same thing with column spaces. Let's say here's my beginning A. I do some row operations. See this bottom row is just twice the top row. I'll end up with this. Well, the basis for this guy is 1, 2. Any multiple of 1, 2 is in this guy's column space. This guy, the basis is 1, 0. Any scalar multiple of this guy is in this guy's column space. Those are obviously not the same column space. So row operations do not maintain column space for what that's worth. Now let's talk about row echelon form. If you have any all 0 rows, they're not even independent of themselves. So we can throw them out. That all 0 rows are not independent. Let's throw them out and let's just look at the non-zero rows. Let's put them all in a linear combination. We're going to add them up vertically here. This is the linear combination of the rows in row echelon form. And we're going to see if they're linearly independent. If you can add these up and get a 0 without making all these C's 0. Or if the only way you could do it is make all the C's 0, then they're linearly independent. And we'll look at this first pivot. These P's are the pivots. This first pivot, it's going to have all zeros below it. So the only way to make that result zero in the sum is to make this C1 zero. So that guy has to be zero. Then if we eliminate that guy, check on the independence of the remaining guys. Well, then you find you got to do the same thing. When this guy's the top row, you have to set C2 to zero because to get this guy to zero. Go through them one at a time, all of them will have to be zero, meaning all the non-zero rows in row echelon form are linearly independent. The zero rows are not linearly independent. This would have been even easier to point out if I'd said, let's get it all the way into reduced row echelon. But we have two facts now. Row operations preserve the rank, and the non-zero rows are linearly independent, and the zero rows are not. Therefore, the rank of a matrix is the number of non-zero rows when you get it into row echelon form. So that we have a method. Use Gaussian elimination to get it into row echelon form and then count the number of non-zero rows. That's the rank. I just showed you why that's true, which took a few tricks. The zero matrix has a rank of zero. Any other matrix has a rank strictly greater than zero. The rank can't be bigger than the smaller of M and N. Yeah, all you really need is the relaxed form of row echelon form. We'll do an example and then we'll talk about the basis of